Hello, in this video we're going to be looking at discrete logarithm problems. Under there is a ECC. Okay, so just like the Diffie-Hellman protocol, this one fits under the same discrete logarithm problem, trying to solve the logs without knowing the power. That's what it's rely on. Okay, so let's have a look at what ECC is. ECC stands for elliptic curve cryptography. So it is quite mathematically heavy on understanding how it works, but hopefully some of my slides behind captures the essence of how ECC works. Okay, but if you do want to get into the mathematical details behind it, I will recommend you to take some math courses for further details, and also there are a lot of materials online. You can have a look. But for this unit, you don't really have to understand the full workings of how ECC works under the hood, but needs to understand exactly how it operates. Okay, so ECC works similar to Diffie-Hellman. Okay, so we'll have a look at how that works. So given a set E consisting of points X and Y in a plane, so hopefully some of your math notations and knowledge, whatever, should be coming back to you. There exists a group operation denoted by plus, but it's not really plus, okay? Such that given 2 points P1 and P2 in E, so E is a plane, okay? So there's 2 points on the plane. P1 plus P2, or well, P1 operation P2 will result in P3, which is also in E. So that's the characteristics that we need as a group operation for ECC. Okay, given point Pi, then we can find points such that the next point was Pi plus Pi, Pi plus Pi plus Pi, and so forth. You can do the operation as many times as you want, and then basically what you end up with is on a plane you have a series of points that can be linked together. And typically, these points actually forms a curve. Okay, so if you search elliptic curves on Google Images, you will see those like funky-looking curves, and those are the points that sit along the lines of elliptic curves, and those values are going to be used. Okay, so we can do this for k minus 1 number of group operations, and we can denote this as k times pi. Basically, we did the operation of pi k times, okay? And the good thing about this is we can easily calculate k times pi, but finding k given k times pi is difficult because you have to try pi plus, and how many times you need to do, okay? So this property is achieved by using elliptic curve. Okay, so let's have an overall workings of that. Alice chooses an integer x, so this integer x is chosen by Alice, which is the private key. Okay, next, Alice then generates y. This is our public key, such that it's x times g. So remember our previous notation of using elliptic curve operation is k times pi. Here k is the x and pi is g. G is standing for generator. Okay. This is the same for Bob. So Bob does the same thing. So Bob will have xb and also generate yb. Okay. So follow the similar process to Diffie-Hellman key exchange. We can exchange the key this way. So Alice calculates k equals xa times yb. Bob sends the yb, and Bob will receive ya and multiply it by xb. Okay, xb is the private key. Okay, so how does that work? Well, what we want to show is that those two equations are equivalent. XA times YB is equivalent to XB times YA. Okay, so XA is YB, but YB can be expanded to XB times G, right? Now we can swap the order around for these operations. It needs to meet some certain criteria, but you use operations that meets those criteria. So now I change the order around so that it's XB times XA times G. Then we can group XA and G together. This will create YA. So we can see that XA times YB is equivalent to XB times YA. So this is same as Bob's key that's been generated. So Alice will generate K. That will be the same as Bob generating K using its own private key. Okay. So Eve has to find either XA or XB from YA, but since YA is XA times G, so you may know G, but you don't know what XA is. So that's the hard part that you need to solve. Okay. So that's pretty much it, understanding ECC without getting too much into mathematical details. And ECC can be used for key exchange. But now we have multiple key exchange algorithms. So why would we want to use ECC instead of other ones? Well, ECC has some advantages. Mainly, the key size can be much smaller than others, while providing equivalent level of security. For instance, if the symmetric key size is 80 bits, the RSA and Diffie-Hellman key size has to be 1024 bits to provide that. Okay, while elliptic curve key size can only be 160 bits, which will provide you the equivalent security. Okay, so this table has been generated by NIST, and as you can see that the number of bits you need for ECC is much smaller than the number of bits you need when using RSA and Diffie-Hellman to achieve the symmetric key size on the left-hand side. Okay, so ECC can reduce the number of key size, but key size does not necessarily reduce the number of operations. Okay, so the running time is different to the key size. Just remember that. Okay, so where can you use ECC? Well, due to the smaller size calculations needed compared to RSA, typically it needs less computational power. The time to compute doesn't necessarily mean it's reduced, but overall, the computation power you need to do is much less because you're handling smaller numbers. Okay, so uses of ECC then includes contactless smart cards. So your student card has ECC, wireless sensor networks, RFIDs, mobile IoT, vehicle communications, and so forth. Anywhere you need a lightweight cryptography, ECC can be used instead. Okay, so hopefully that clears up a bit of a difference between those guys. So here we also cover the difference between symmetric and asymmetric as a summary. Well, symmetric and asymmetric ciphers, they have main differences as shown on those tables. Okay, so depending on the need of what information you need to exchange, you can always have a look in those comparison tables and pick the one that best suits your needs. Okay, but typically you want to use both of them. So you will use the asymmetric ciphers to distribute the key, for example, RSA, Diffie-Hellman, or ECDH RSA, and so forth. And once the keys are distributed, then you use the symmetric key cipher, such as AES, which can encrypt and decrypt messages much faster. And this is also the how most security protocols use in modern time. So hopefully that described much about the basics of ECC and also a bit comparisons with symmetric and asymmetric ciphers. Otherwise, I will see you in the next video. Bye-bye.